Okay, so this is the version of a talk that I gave on September 9th, 2021 in the math education department at Virginia Tech. And so I'm doing another version of this completely digitally, just so I can have wider distribution of it. And so this talk concerns a particular kind of representation of complex vector spaces and a brief kind of exploration into some basic properties and some research directions it can be used in with regard to math education itself. And so we are going to go through just the basic representation of the vector space C2, talk about some of the topological properties we can get with the Hermeitan product, have some additional questions with regards to the actual mathematics here, and some questions about math education as well. So just to review, a finite dimensional vector space over a field K can typically be represented by what's called coordinate space, which is just a list of elements from the field K. And so the length of the list is the dimension of the vector space, typically, well, always. And we have the structure of addition we add everything component-wise, and to scale a vector, we just multiply every entry by the element from the field. And in the United States, specifically, a linear algebra class always takes the field to be over the real numbers. And something that is very familiar with a lot of undergrads is that it's very easy to visualize one dimension, two real dimensions, and three real dimensions, because three real dimensions is where we live, and we can capture lower dimensions with like a piece of paper or wire or string. But once we get to four real dimensions, then our psychology kind of breaks, and it's very difficult, if not impossible, for people to quote-unquote visualize four dimensions in terms of generalizing how we think about two or three dimensions. And so now to just briefly review the complex plane, we have that it is just the underlying set of R2, the plane with addition and multiplication to give the structure of a field. And we also note that C comes equipped with an additional operation that's called complex conjugation, which takes just the number a plus bi to a minus bi and is denoted z bar, where z is just a typical variable for a complex number. And it's important because it's the one non-trivial field automorphism of C. Notably, non-trivial field automorphisms don't exist for R and Q. And addition of complex numbers is really easy to visualize in just the typical tip-to-tail fashion that we're all used to. And complex multiplication also admits a geometric interpretation where you scale a vector by a certain amount and then add the angles. And this is seen when we multiply complex numbers in terms of their polar form. You can just see that the magnitudes are being multiplied and the angles are being added. And so, in a sense, a complex vector space can be thought to have three underlying sets that are different in these kind of subtle ways, right? Where we have n copies of C, n copies of R2, or 2n copies of R. And for this presentation we'll be showing you, we will be using the representation of n copies of R2. N copies of R2. Okay, so now I'm just going to briefly... Okay, so now just for kind of editing purposes, I'd encourage you to just get out some paper and follow along with me as I display what's going on, just because I'm not going to really be able to have both this representation and the slides on screen at the same time. And so what you do is you draw the complex plane, and we want to represent a vector, let's call it z sub circle, comma, z sub star in C2. And the reason for these kind of unconventional subscripts is going to be obvious in a second, because what we do is we represent it by a pair of complex numbers in C or R2, and this pair is a single vector in C2, and it will be very useful to come up with this other function we call arg of z0 z star to be the angle made starting at z circle going counterclockwise to z star. So it would be an angle like that. And so this is, you can think of it as taking the natural orientation of the complex plane into account when we move up to higher dimensions. And so to visualize something in C3, right, we do something like z dagger into C3. All we do is add one more vector. And kind of paradoxically, in this quote-unquote visualization, it's easier to visualize additional complex dimensions than it is to envision complex real dimensions. And so that's the basic principle going on here. And so from here, what we have is that within C2, we have that two vectors, A and B, are going to be linearly dependent if and only if the ratio of the length of the components are the same between them and the argument of the components is the same. And this is kind of up to some as of yet undetermined convention when one of the components is 0, because obviously the lengths and angles don't really make sense in that case, but it's not something that I think we should be too worried about. And so we have that one-dimensional subspaces of C2 are represented by a pair of vectors in R2 with a unique angle and ratio of lengths. This is also how a vector is determined to be in the eigenspace for a given linear transformation, is to just see if two vectors share the angle and ratio of lengths. And all of this follows from how we multiply a complex vector by a complex scalar, because the scalar goes into each component and the scalar rotates each component by the same amount angle-wise, scales each the same lengthwise, and so this is where the result comes from. And so for general Cn, the one-dimensional subspaces are determined by, I think, and choose two basically amounts of data in terms of the ratios, and choose two amounts of data in terms of the angles to keep track of. And a kind of open question here is, what geometric data characterizes two-dimensional subspaces of C3, where in the two-dimensional case, going a dimension lower gives this very nice characterization, and I'm hoping that when we ask a similar question for C3, the answer is going to turn out to be similarly elegant or nice to keep track of. And so now I want to talk about the topology of complex vector spaces, and this is all based on a Math Exchange comment by Elizabeth S.Q. Goodman. I'll leave a link to that in the description below. And so for complex vectors, we say that, and this last comma should be a dot, we say that the product of z and w is the sum of the component of the first times the complex conjugate of the respective component of the second. And this particular product we denote as just h of v and w for Hermeitan. And for Cn and a vector z, we denote z perp w to mean that the Hermeitan product of the two is 0, and kind of like in the typical inner product sense, we denote the complex orthogonal complement to be just everything that is orthogonal to a given vector. And H has almost all of the same properties as a regular inner product, with bilinearity, positive definiteness, and non-degeneracy, but instead of the symmetry axiom, we replace it with skew symmetry, which means that when you swap two arguments, then the result is the conjugate of the original. And since H is complex valued, it can be decomposed into a real and imaginary part, and those are denoted as G plus IW, where both G and W, or it would be more accurate to say omega, are both real valued, but the I denotes the complex part. And so it's a kind of relatively simple exercise to see that G is dot product in the real sense if you consider a vector in Cn to be a vector in R2n. And the imaginary product is what's called a symplectic product, and there is an entire field of geometry dedicated to studying spaces with this kind of structure endowed upon it. And an important fact, a very simple fact to show, is that omega of A times IB is the same as G of A times B. And so we have that two vectors in Cn are complex orthogonal if and only if they're orthogonal in the real sense and orthogonal in the symplectic sense. And for a given vector v, the real orthogonal complement is going to be a three-dimensional real subspace, and the same holds for the symplectic complement. And so they are going to interact on a set that has two real dimensions and therefore one complex dimension. And so some additional math questions we have here is, does this presentation help us to see that every complex matrix has an eigenvector, right? Does this presentation give us a kind of nice geometric proof to the fact? Next is, within C2, is there just a nice pair of vectors that are orthogonal in the real sense but not the symplectic sense, and vice versa, orthogonal in the symplectic sense but not the real sense? And now, kind of in the spirit of Erdős, I have some bounties for some questions that I really want the answers for, which is, what is a nice interpretation of symplectic orthogonality? And this is, of course, within the context of this representation I described. Next, is there a correspondence between C2 and R4 that gives a necessary and sufficient geometric interpretation of real orthogonality? Just because this is a kind of novel presentation, and yeah, like, it's easy to say what is real orthogonal when we think about it how we usually do, but in this new presentation, I don't know if there is an easy way to determine it or not. And then we repeat the previous question for arbitrary Cn, like when I give you a complex vector of 3 dimensions, can you give me another vector really easily that's going to be real orthogonal to it? Okay, and so in terms of math education, I can see this going in multiple directions, which is, one is the notion of novel tasks, which is how readily do students with different knowledge sets react when presented with this, right? Do they see it as a legitimate context for linear algebra, or do they see it as something like kind of like linear algebra, but not really? And how does a student's experience either entrench this view or detach them from this view? Another is, how do students bring their intuition on how to quote-unquote move in CN, right? Can they envision what a path looks like? A path being a map from the interval 0, 1 into the space, a continuous map. Next is the various conceptions of complex vector spaces themselves, right? Do they think of Cn R2 to the n, or R to the 2n, and R2 to the n as different objects? Do they see them as just like all as the same kind of underlying set, but with just different structures, or do they just not really care about the differences at all? And then, in terms of generalizing real vector spaces themselves, do they see this presentation as a legitimate generalization of Euclidean space, of higher dimensional Euclidean space, or do they see it as something completely different? And then in terms of something like working memory, if it becomes it's relatively simple to add another vector to this to get higher dimensions. And the kind of question then is, can humans add as many vectors as they want and keep their kind of conceptual schemes the same, or can you kind of overload them by adding quote-unquote too many dimensions? And then if so, then what is the kind of limit of their cognition there? And finally, would this be helpful to mathematicians, and who already thinks this way? Because I have a hard time believing that this is a truly original idea, and I would like to know, what about the kind of current state of mathematics education leads us to not think of it this way, and if there is a group of people, either culturally in the sense of what they study, or just culturally in terms of just the wider culture that they inhabit and how they see and understand the world, that would lead them to think like this, right? What are the cultural components that lead people to either accept this representation and to discover it by themselves, or to not? And so that's really the extent of this. Thanks for listening.